So chapter 18 will officially the final chapter of our CCENT discussion. And then we get into some of the more advanced discussions when we start to get into our CCNA topics. RIP, the Routing Information Protocol. As I mentioned before, we're going to be using our topology here to implement this RIP architecture. And this is, we've already talked about most of the theoretical concepts of RIP, but now we need to talk about how do we implement it, how do we troubleshoot it, how do we verify it, etc. Now, the Routing Information Protocol, like I said, not really that important, not that critical, but honestly, by going through and learning a few things about RIP, we're actually also going to be learning about things like OSPF and EIGRP. Now, the way this chapter is structured is a little bit different than the chapters we've seen in the past. What we do in this particular chapter is we have these different implementations, and it's kind of a working chapter. We do the implementation, we talk about that implementation. We go on to the next section, we do another piece of implementation, we talk about it. So here's what I would like you guys to do as part of this exercise. Pull up your topology and go ahead and implement what you see on the screen here, which should only take you a couple of minutes. Don't worry about the understanding of it yet. Just make sure that you put it in the same way. And then as we progress through the chapter and as we go through each slide here, I'm going to describe what the purpose of these commands are, what the goal of these commands are, and why we implemented them. And then we'll move on to the next step. Okay? So I'm going to go ahead and start to do the implementation here. Let me go into my router. First thing is router RIP. Now, if I do router question mark, you'll notice that I have a few options. I can do router BGP, router OSPF, router EIGRP. Any of these that I execute, router RIP, router EIGRP, router OSPF, does not mean that I'm turning on the protocol. So if I type router RIP, it doesn't enable the routing protocol. All it does is allow me to go into router configuration mode, which allows me to configure the properties of RIP. The commands that we actually execute that enable the protocol are these network commands. All right? Now, the network commands is what people get the most confused about when they're introduced to these routing protocols for the first time. And I want to spend a little bit of time talking about that because OSPF uses network statements. EIGRP uses network statements. BGP uses network statements, and so on. As you can see, these are pretty important. The network statement does two things. The network statement does two things. The first thing it does is it enables the routing protocol, whichever one it is, OSPF, EIGRP, RIP, whatever, it enables the routing protocol on the interface that's included in the statement. So that 10 interface is now running RIP. That 11 interface is now running RIP. That 200 interface is now running RIP. But it also does something else. It tells the routing protocol which networks to include in the advertisements. Oh, it's a very distinct difference. When you look at this topology diagram, if I was to say, okay, turn RIP on the interfaces that are necessary, what would you do? You would probably say, well, I really only need to run RIP on this link because the whole point of RIP is to share routing information. Agreed? And the only other router that I need to share routing information with is that one. But see, the problem is if I only include a network statement for that interface, the second thing doesn't happen. Remember, I said the second thing is the network statement tells the router which networks to include in the advertisements. So if I were to exclude network statements for the 10 network and the 11 network, even though I would be exchanging information with the other router, I would not be telling the other router about the 10 network or the 11 network. Does that make sense? Now you also notice that the top router, or the left router, had 3 separate network statements. The bottom router only had 2. That is because when we enter our network statements in with RIP, we simply put it in the classful version of the networks. The classful version. That's why you see a 200.0 here, because this is a Class C network. Only the first 3 octets are part of the network. Even though it is a subnetwork, from a classful perspective, the network ID is 209.165.200. Now, this is not because RIP is classful. Because the other thing I want to make clear is that the network statements do not identify how the networks are actually advertised. Think of those network statements basically as a light switch. For example, the 10 statement here. That includes that network and that network. So by putting in this network statement, I've essentially turned on that light switch that says, now this network and this network are participating in RIP. I'll explain more about that when we get into some of the better protocols a little bit later on. RIP, very simple, basic protocol. So let me go ahead and implement my network statements here. Network 192.168.10.0, network 192.168.11.0, network 209.165.200.0. And I'll go into my router on the right, config T, router RIP, network 10.0.0.0, network 209.165.200.0. All right. Now, essentially, I've actually completely configured RIP. Now, it's not the best form of RIP. There are a lot of inefficiencies in this design and this implementation, not to mention a lot of security risks, but we've implemented RIP. So let's start to do some of our verifications. Let's go into the router on the left. All right. What about that other test? Well, I have to do it eventually. Okay. Show IP route RIP. Okay. Can we get that router hooked up over there? thinQtank? Yeah. And as you can see, I'm actually learning about the network on the other side. A little bit of a problem though here, right? What's the problem? We're not seeing the subnets. We're seeing 10.0.0.0/8. What does the 120 represent? What does the 120 represent? That is the administrative distance of RIP. What does the 1 represent? That is the metric. So you look at the diagram. Yes, it is going to cost me 1 hop to get to those 10 networks. 1 hop to get to the 10 networks. All right? So we are getting information that's useful. Here is the next hop IP address. This is how old the route is, how long the route's been in our database, and this is the interface that I go out of to reach the next hop. Now, if I go to the other router, show IP route, RIP. I see both networks. Why am I seeing both networks on this router, but I only saw a single network on the other router? Why am I seeing both networks on this router, but I only saw a single network on the other router? Because these networks were already class full. These networks are already class full. They're 192 networks with a /24 mask. So they're being advertised as they're configured. They're being advertised as they're configured. So let's do a little investigation and let's find out why we're not seeing these subnets. There's a command, a new command I want to introduce to you guys. This is pretty much one of the most important commands that we can use if we're working with routing protocols. Show IP protocols. Everybody go into router number 1 and run the command show IP protocols. Okay. The routing protocol in operation is RIP. That makes sense. Updates are being sent out every 30 seconds. That makes sense. That's what RIP does. We have various timers here. These timers are used to manage convergence. Remember, RIP is a distance vector protocol. As such, it is well, it's a little bit suspicious about what happens on the network, especially when there are changes that happen in the network. So what this means is if routes go away, they become invalid after 180 seconds. I'm going to hold them in my database for another 180 seconds, and I'm only going to flush them from the database after 240 seconds expired. So when we talk about slow converging, that's what we mean. In order for RIP to converge, we're looking at about 180 to 240 seconds of time. You also notice that, and this is the key, we're running RIP version 1. By default, Cisco, when you implement RIP, is RIP version 1. Now this tends to make a little bit more sense. It makes sense why we didn't see the subnets, because RIP version 1 does not support subnetting. Everything is done classfully. A couple of other things I want to point out here. Automatic network summarization is in effect. I'm going to explain more about that in a little bit. That's actually a bad thing as well. We actually have an exercise in this chapter where we investigate that concept of automatic network summarization. Maximum paths of 4. You'll see this throughout all of our protocols with the exception of BGP. Maximum paths of 4 means that I will load balance up to 4 paths if they have the same metric. We don't have any redundant paths in our topology, so we won't see any load balancing in our topology, but this says I can load balance up to 4 paths by default. Now, if I say maximum paths of 1, what does that mean? It's a configurable value, by the way. If I go in and change that value to 1, what does that mean? If I change that value to 1, it means no load balancing, only use 1 path. The minimum is 1. The maximum is 16. The default is 4. You'll also notice that you can see which interfaces are running RIP. That's important to understand later on. We'll see something about that and why that's bad. So even though we only did 3 or 4 commands to turn on the protocol, we can already see that various configurations are vastly inadequate for a real network. We don't want to run RIP version 1. We don't want automatic network summarization. We don't want classful versus classless and all that. The administrative distance is 120. The gateway, in other words, the interface that I've established a neighbor relationship on, is 226. Gateway simply means that I received a routing update from that address, which we did. We received a routing update from that neighbor. So that neighbor is a gateway for reachability. Would that maximum path also have a maximum value of 15? No. Maximum paths does not mean hop count. Maximum paths does not mean hop count. What it means is how many paths can I load balance given that they have the same metric. Let me demonstrate with RIP because it's actually pretty easy to demonstrate with RIP. Let's say that I have a router here, 1 connection, 2 connections, 3 connections, 4, and each of these connections have a link to my destination network. Load balancing is the concept of each of these paths having the same metric and using all paths at the same time to send and receive information. You can see how that doesn't really have any effect on the hop count because the hop count was still only 1. If I set a maximum path value of 1, same topology, 1, 2, 3, 4, set a maximum path of 1, then what RIP would do is it would use 1 path. The other paths might be available for redundancy, but I would send all of my traffic over a single path, as opposed to sending 1 packet here, 1 packet here, 1 packet here, 1 packet here. Okay? So the minimum value you can have here is 1. For IPv4, the maximum value you can have is 16. Completely unrelated to the hop limit in RIP. Well, let's start to fix some of these problems. First of all, I don't want to be running RIP version 1 because it doesn't support subnets. So how do I stop running RIP version 1? I have to switch to version 2. Here's a debug. We're not going to run a debug right now, but let me explain what this debug is showing me. When you run the command debug IP RIP, what you're seeing is the actual updates that are going back and forth. And what I wanted to point out is the destination address for the updates, number 1, and that it's version 1. So 2 different ways we were able to find out whether or not we're running RIP version 1 or RIP version 2. All right. How do I fix that? It's actually very simple. You go under router RIP and you implement RIP version 2. So let's go ahead and do that on both of our routers. Config T, router RIP, version 2. Config T, router RIP, version 2. I'll give you guys a second to implement that. So now that we've implemented RIP version 2, that means we should see our subnets, right? Well, if you go back into router 1 or router 2, actually let's go to router 1, show IP route RIP, we still only see the /8. Dang it. We're supposed to be running VLSM. We're supposed to be able to support subnets. If I do a show IP protocols, I can see that I'm running version 2. I'm sending and receiving RIP version 2. But this right here is a bad thing. For some reason, and Cisco did the same thing, by the way, but for some reason, the makers of RIP version 2 decided that even though we support subnetting, let's go ahead and make the protocol act classfully by default, even though it's classless. Automatic network summarization means summarizing to major network boundaries. EIGRP used to have this enabled by default in its environment as well. but in the newer versions of EIGRP, when I say newer, I mean over the last few years, they actually make they disable this feature by default. Why would you have a classless protocol act classfully? Doesn't make a whole lot of sense. So you had asked a question earlier about, do these routers do summarization automatically? Right, we were talking about route summarization. Yeah. This is the exception to that. But this is a bad exception. Because it doesn't do summarization mathematically. It doesn't calculate summary boundaries efficiently. It just assumes major network boundaries. It just assumes major network boundaries. So obviously now we have to turn off that quote-unquote feature. The way we turn off that feature is we use the command no auto-summary. So let's go ahead and implement that. Go into router 1, config T, router RIP, no auto-summary. Let's go to our other router, config T, router RIP, no auto-summary. Now, hopefully, we should see our subnets. Show IP route RIP, and sure enough, I now see my subnets. Unfortunately, because RIP is stupid, it also keeps the original route for a very short period of time, maybe 3 minutes or so. That route is in a hold down state. It's trying to figure out, is this route going to stay there? Is it not going to stay there? It's not being advertised anymore, but that's maybe because my neighbor made a mistake, and who knows, it might come back. So I'm going to keep that route in there for a period of time, but eventually that route will disappear. And we'll have our classless routes, which is what we want to see. So quick review of what we've done so far. Show run, go down to the RIP section, router RIP, took me into configuration mode. My network statements turned the protocol on the respective interfaces. Version 2, of course, allowed us to switch to RIP version 2. No auto summary turned off the automatic summarization at major network boundaries. We're almost done. Remember, we're not going to be talking about the authentication piece. That would be another step that we would implement down the road, but we're not quite done yet. The next thing I want you guys to do is I want you to take a look at show IP protocols. Show IP protocols. Which interfaces am I sending RIP advertisements out of? Every 60 seconds. 30 seconds, excuse me. Which interfaces am I sending advertisements out of? All the connected interfaces, all the interfaces that I turned RIP on. Now, if I look at my topology, here's my topology, there aren't any routers on the gigabit Ethernet networks. I'm sending routing updates out of my gigabit Ethernet networks every 30 seconds, and there's nobody there to hear them. Number one, I'm wasting resources. Number two, it's a security risk, because somebody could be in that network listening for those advertisements, and they could glean information about our topology. Like we're running RIP, like we're running RIP version 2, like we're running different protocols, and these are the networks that we're advertising. So what I would like to be able to do is have the ability to suppress those routing updates from going out those interfaces, but at the same time still allow those networks to be advertised. Now, this is an important concept because this concept exists in OSPF, it exists in EIGRP, and it exists in RIP. It's called passive interface. If I was to remove the network statements for those two networks from my configuration, then nobody would learn about them because those networks would not get advertised. But by using the passive interface command, what I'm telling RIP to do is stop sending out updates out those interfaces, but still allow those networks to be advertised to the rest of the world. So essentially, by making an interface passive, we're reducing the amount of load on our network, okay? We're also eliminating how many interfaces are actually sending the advertisements. So let's go ahead and make your interfaces passive. You won't see any effective difference from the routing updates, at least from the other router, because you wouldn't make your serial interface passive. If you made your serial interface passive, then the neighbors wouldn't exchange information. You might be able to receive information, but you're not going to be sending information. So you definitely don't want to make your serial interfaces passive. All right? Now there's two ways to implement the passive option. You can make the interfaces passive, or you can make everything passive and then make the interfaces that are not passive, not passive. Both of them have effectively the same result. It's just a matter of which one is better, which one's worse, based on the number of interfaces. If you have 100 interfaces, well, let's be realistic. If you have 7 interfaces that are passive and one that's not passive, then it's better to use the bottom option. If you have 1 interface that's passive and 7 that are not, it's better to use the top option. It's just a matter of how many commands that you have to type in. Outside of authentication, and some other really advanced functions of RIP, that's pretty much it. It's extremely simple to implement this dynamic routing protocol. And actually, that's really what you're going to find with OSPF. You're going to find this with EIGRP. It's easy. But doing the implementation and understanding the impact of the configurations are completely different things. People often ask me, what is the difference between a network administrator and a network engineer? And a network administrator can put these commands in. A network engineer understands what those commands mean. They understand what the impact is. They understand what the design requirements are, etc. Not just these commands, but any command. All right? So how do we verify our passive interface operation? If I do a show IP protocols, I can see listed which interfaces are now passive. And if I do a debug, I can now see that the only interface that RIP updates are being sent out of is the interface that's not passive. Make sense? All right. So that officially concludes CCENT.